Nenomatica, where mathematics meets YouTube excellence. Welcome to our mathematics video. Today, we'll explore a fundamental theorem about basic inequalities. We'll be proving Theorem 10 about basic inequalities. Let's start by understanding what the theorem states. For all real numbers, a and b, we have the inequality. The arithmetic mean of a and b is less than or equal to the square root of their quadratic mean. Alternatively, we can express this as the square of their arithmetic mean is less than or equal to their quadratic mean. Let's focus on the first part of the theorem and prove it step by step. We start with the inequality we want to prove. To prove this inequality, we'll square both sides, since the square function is increasing for positive numbers. When we square both sides, we get the square of the arithmetic mean is less than or equal to the quadratic mean. Now, let's expand the left side of the inequality. The square of a plus b over 2 equals a squared plus 2ab plus b squared, all divided by 4. To make it easier to compare, let's multiply both sides by 4. This gives us a squared plus 2ab plus b squared is less than or equal to 2 times a squared plus b squared. Let's simplify further. We can subtract 2a squared and 2b squared from both sides, which gives us 4ab is less than or equal to 2a squared plus 2b squared. We can divide both sides by 2 to simplify. This gives us 2ab is less than or equal to a squared plus b squared. Rearranging, we get a squared plus b squared minus 2ab is greater than or equal to 0. Now, we recognize that this expression is actually the square of a minus b. So we have a minus b quantity squared is greater than or equal to 0. And this is always true for any real numbers, a and b, since the square of any real number is always non-negative. Therefore, the last inequality is always true, which means our original inequality is also always true. The theorem is proved. Let's add a note. If it equals b, then equality holds in our original inequality. This means that the arithmetic mean equals the quadratic mean when the two numbers are the same. The theorem can be generalized. We can extend this inequality to higher powers and to multiple variables. For example, for the nth power of the arithmetic mean is less than or equal to the nth power mean when n is greater than or equal to 1. And for multiple variables, the nth power of the sum of m variables divided by m is less than or equal to the sum of the nth powers divided by m when n is greater than or equal to 1. Welcome to our math video. Today we're going to explore an important theorem in inequalities mathematics. Let's start by looking at the statement of the theorem. The theorem states, if a sub 1, a sub 2, up to a sub n are all greater than 0, then the product of 1 plus a sub 1 multiplied by 1 plus a sub 2, and so on until 1 plus a sub n is greater than or equal to 2 raised to the power of n multiplied by the square root of a sub 1 times a sub 2 times, up to a sub n. Now, let's move on to the proof of this theorem. We'll begin with a basic inequality from the AMGM inequality. For any two positive numbers, a and b, a plus b is greater than or equal to 2 times the square root of a times b. Now, let's apply this basic inequality to each of the terms in our theorem. First, let's take 1 plus a sub 1. We'll set 1 as the first term and a sub 1 as the second term. So, 1 plus a sub 1 is greater than or equal to 2 times the square root of 1 times a sub 1, which simplifies to 2 times the square root of a sub 1. Similarly, we can apply the same inequality to the other terms. For 1 plus a sub 2, we get that it's greater than or equal to 2 times the square root of a sub 2. And for 1 plus a sub n, we get that it's greater than or equal to 2 times the square root of a sub n. The next step in our proof is to multiply all these inequalities together. When we multiply the left sides and the right sides of all these inequalities, we maintain the inequality sign because all terms are positive. After multiplying, we get on the left side the product of 1 plus a sub 1 times 1 plus a sub 2, and so on until 1 plus a sub n. On the right side, we get 2 to the power of n times the product of all the square roots. Now, let's simplify the right side of our inequality. The product of n factors of 2 can be written as 2 to the power of n, and the product of the square roots can be written as the square root of the product of all the a's. And with that, we've completed the proof of our theorem. We've shown that if a sub 1, a sub 2, up to a sub n are all greater than 0, then the product of 1 plus a sub 1 multiplied by 1 plus a sub 2, and so on until 1 plus a sub n is greater than or equal to 2 raised to the power of n, multiplied by the square root of the product of all the a's. Let's look at two important special cases of this theorem. First, if the product of all the a's equals 1, then the inequality simplifies to the product of 1 plus a sub 1 times 1 plus a sub 2, and so on until 1 plus a sub n is greater than or equal to 2 to the power of n. Second, for all positive values of a sub 1, a sub 2, and so on until a sub n, we also have another important inequality. The product of 1 plus a sub 1 times 1 plus a sub 2, and so on until 1 plus a sub n is greater than or equal to 1 plus the sum of all the a's. This concludes our exploration of this basic inequality theorem, an important result in the study of inequalities. The last inequality we mentioned is known as Weierstrass's inequality, and the a's are greater than or equal to -1. Welcome to this Math GPT video on basic inequalities. Today we're going to explore an important inequality in mathematics known as the Cauchy-Schwarz inequality, or Theorem 12 of basic inequalities. Let's start by stating the theorem. For all a sub I and b sub I belonging to the real numbers, the following inequality holds. The sum of squares of a sub I times the sum of squares of b sub I is greater than or equal to the square of the sum of the products a sub I times b sub I. Now, let's go through the proof of this theorem step by step. The proof uses the Lagrange identity, which gives us a way to rewrite the Cauchy-Schwarz inequality. The Lagrange identity can be written as follows. The product of the sum of squares of a sub I and the sum of squares of b sub I equals the square of the sum of products of a sub I and b sub I plus a sum of squared differences. Now, let's look at the second part of this equation. The summation of a sub I times b sub j minus a sub j times b sub I, all squared, is always non-negative because it's a sum of squares. Therefore, we can remove this part from the right side of the equation, which would give us an inequality instead of an equality. By removing this non-negative term from the right side of our equation, we obtain the inequality. So we can say that the product of the sums of squares is greater than or equal to the square of the sum of products. This is exactly the Cauchy-Schwarz inequality that we wanted to prove. Let's look at a special case of this theorem when n equals 2. This gives us a more familiar form of the Cauchy-Schwarz inequality that you might have seen before. Let's consider an application of this inequality. If ax plus by equals k, where k is a constant, then x squared plus y squared is greater than or equal to k squared divided by a squared plus b squared. To prove this, we apply the Cauchy-Schwarz inequality to our constraint. By the inequality, we have a squared plus b squared multiplied by x squared plus y squared is greater than or equal to the square of ax plus by. But ax plus by equals k, so the square of that is k squared. Dividing both sides by a squared plus b squared, we get our result x squared plus y squared is greater than or equal to k squared divided by a squared plus b squared. An important observation here is that if ax plus by equals k, then the minimum value of x squared plus y squared is k squared divided by a squared plus b squared. This minimum is achieved when the ratio of x to y is the same as the ratio of a to b. We can also write this as a conditional statement. If ax plus by equals k, then the minimum value of x squared plus y squared equals k squared divided by a squared plus b squared. Let's summarize what we've learned about the Cauchy-Schwarz inequality. First, we stated the general form of the inequality for any number of variables. Second, we proved it using the Lagrange identity, showing that removing a non-negative term gives us the desired inequality. Third, we looked at the special case when n equals 2 and saw an application involving the minimum value of a quadratic expression subject to a linear constraint. This inequality has many applications in various fields of mathematics, physics, and statistics. It's a powerful tool for optimization problems and establishing relationships between different quantities. Welcome to our math lesson on basic inequalities. Today we're going to explore an important theorem in mathematical inequalities and understand its proof step by step. Let's begin with the theorem statement. For all a 1, a 2, and so on up to an, where each a is a positive real number, if the product of all these numbers equals 1, then the sum of all these numbers is greater than or equal to n. Now, let's see the proof of this theorem. We'll start with the case where n equals 2. In this case, we need to prove that if a 1 times a 2 equals 1, then a 1 plus a 2 is greater than or equal to 2. Let me explain why a 1 plus 1 over a 1 is greater than or equal to 2. This is because of the AMGM inequality, which states that the arithmetic mean is greater than or equal to the geometric mean. For two positive numbers, this means that their sum divided by 2 is greater than or equal to the square root of their product. Now, let's consider the general case. We'll use an inductive approach. Let's assume that the statement is true for a given value of n. That is, if the product of n positive real numbers equals 1, then their sum is greater than or equal to n. Let's examine a specific case where n equals 3. We have 3 positive real numbers, a, b, and c, if a times b times c divided by a times b times c equals 1, which simplifies to a over b times b over c times c over a equals 1, then the sum over b plus c over a is greater than or equal to 3. Let's visualize the inequality. We'll represent our 3 variables a, b, and c as the lengths of sides of a triangle. The inequality then states that the sum of the ratios of consecutive sides is at least 3. To prove this inequality, we can apply the Cauchy-Schwarz inequality. This inequality states that the square of the dot product of 2 vectors is less than or equal to the product of their squared lengths. Another useful inequality is the AMHM inequality, which states that the arithmetic mean of positive numbers is greater than or equal to their harmonic mean. This is a direct consequence of the AMGM inequality we saw earlier. Now, let's look at a note about our theorem. If a 1, a 2, and so on up to an are all positive real numbers with the same sign, then the sum of the ratios of consecutive terms is greater than or equal to n. An important special case is when a, b, and c are the sides of a triangle. Then a over b over c plus c over a is greater than or equal to 3. Let's verify our inequality using the AMGM inequality once more. For any 3 positive numbers, the arithmetic mean is greater than or equal to the geometric mean. If we apply this to a over b, b over c, and c over a, we get the sum of a over b, b over c, and c over a divided by 3 is greater than or equal to the cube root of their product. To summarize what we've learned today, first, we proved that for 2 positive real numbers whose product is 1, their sum is at least 2, with equality when the numbers are equal. Then, we showed that for n positive real numbers whose product is 1, their sum is at least n, with equality when all numbers are equal. We also examined the special case where the numbers represent the sides of a triangle, giving us the inequality that the sum of the ratios of consecutive sides is at least 3. These inequalities are powerful tools in mathematical problem solving and have many applications in geometry and optimization. Welcome to our video on basic inequalities. Today, we're going to explore 2 important theorems about inequalities involving exponential expressions. Let's start with our first theorem. If a is greater than b, and both are greater than 0, then when x is greater than 0, a raised to the power of x is greater than b raised to the power of x. Now, let's prove this first theorem. We start with the given condition that a is greater than b, and both are greater than 0. Let's define a function, f of x equals a to the power of x. We can find the derivative of this function, which is the natural log of a times a to the power of x. Since we're told that a is greater than 0, and we're considering x greater than 0, we know that a to the power of x is always positive. Also, since a is greater than 0, the natural logarithm of a is well defined. When a is greater than 1, the natural log of a is positive, making the derivative positive. So f of x is strictly increasing. Similarly, for b, we can show that g of x equals b to the power of x is also strictly increasing when b is greater than 1. Now, since a is greater than b, and both are greater than 0, and we're considering x greater than 0, we can compare the values of a to the power of x and b to the power of x. Since both functions are strictly increasing for a and b greater than 1, and is greater than b, we can conclude that a to the power of x is greater than b to the power of x for any positive value of x. This proves our first theorem. If a is greater than b, and both are greater than 0, then a to the power of x is greater than b to the power of x when x is greater than 0. Let's visualize this theorem with a specific example. Let's take a equals 3 and b equals 2, both of which are positive with a greater than b. If we plot the functions f of x equals 3 to the power of x and g of x equals 2 to the power of x, we can see that for all x greater than 0, the curve for 3 to the power of x, we can see that for all x greater than 0, the curve for 3 to the power of x always stays above the curve for 2 to the power of x. This confirms our theorem visually. Now, let's look at our second theorem. This theorem states that if x is greater than y, and both are greater than 0, then, if it is greater than 1, then a to the power of x is greater than a to the power of y. And if it is between 0 and 1, then a to the power of x is less than a to the power of y. Let's prove the second theorem. Given that x is greater than y, and both are greater than 0, we'll analyze two cases based on the value of a. Case 1, when it is greater than 1. If it is greater than 1, then the natural log of a is positive, since x is greater than y. And the natural log of a is positive, we have x times the natural log of a is greater than y times the natural log of a. Taking the exponential of both sides, we get a to the power of x is greater than a to the power of y, which proves the first case. Case 2, when it is between 0 and 1. If it is between 0 and 1, then the natural log of it is negative, since x is greater than y. And the natural log of a is negative, we have x times the natural log of a is less than y times the natural log of a. Taking the exponential of both sides, we get a to the power of x is less than a to the power of y, which proves the second case. This completes our proof of the second theorem. Let's visualize the second theorem with examples. For the first case, let's take a equals 2, which is greater than 1, and compare the values of 2 to the power of x for different positive values of x. As we can see on the graph, when it is 2, which is greater than 1, the function a to the power of x is increasing. So for x equals 3 and y equals 1, both of which are positive with x greater than y, we have 2 to the power of 3 equals 8, which is greater than 2 to the power of 1 equals 2. For the second case, let's take a equals 0.5, which is between 0 and 1, and again compare the values of 0.5 to the power of x for different positive values of x. As we can see on this graph, when it is 0.5, which is between 0 and 1, the function a to the power of x is decreasing. As we can see on this graph, when it is 0.5, which is between 0 and 1, the function a to the power of x is decreasing. So for x equals 3 and y equals 1, we have 0.5 to the power of 3 equals 0.125, which is less than 0.5 to the power of 1 equals 0.5. Let's summarize what we've learned about these basic inequalities. For our first theorem, we showed that if it is greater than b and both are greater than 0, then when x is greater than 0, a to the power of x is greater than b to the power of x. For our second theorem, we showed that if x is greater than y and both are greater than 0, then, if it is greater than 1, a to the power of x is greater than a to the power of y. If it is between 0 and 1, a to the power of x is less than a to the power of y. These theorems are fundamental in understanding how exponential functions behave with different bases and different exponents, and they have many applications in mathematics. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. Nenomatica, where mathematics meets YouTube excellence.